Okay, thank you for that introduction. I'll start off this first plain dev day by trying to paint a broad picture of LLM assisted development. And so we are all interested in knowing how can LLMs help us write better software or bigger software or faster write it. And so I chose this provocative title because we all like to 10x things. So how can we 10x software development with LLMs? Shortly, brief introduction about me. I have a background as a researcher in computational algebra from the Technical University of Denmark. And then I found out that I wanted to get my hands dirty and actually build stuff. So I was fortunate enough to join GitHub just at the time where the what became the Copilot, GitHub Copilot, was sort of incepted. And so I was a very early team member on that project and helped build it. After that, I went on to build other interesting projects in GitHub, including Spec-driven, which I'll talk a lot about today. Then in 2024, I left GitHub to join as a founding engineer of a new startup called Expo, which I won't talk that much about today. But many of my fellow Copilot pioneers are also at that company. And then since the beginning of 2025, Johan contacted me, and we found out that we had this shared interest in spec-driven development, and he invited me to become technical advisor and investor in CodePlane. So just a quick word about what we do at Expo. This is an AI security startup. So the product we have is completely autonomous pen tests. So we try to hack the customer's site, and if we succeed, we tell them how we did it, and then they can close the security gaps. And I think that's relevant for today. It's sort of the other end of software development lifecycle. If you 10x software production, you also have to 10x software security testing. So that's essentially what we're trying to do in Expo. Right. Not more about Expo. Let's return to when Spec-driven was first thought of. So this is a very, very long time ago in AI land. So that's around May 2023. I put down here a timeline. To me, it just doesn't really fit in my brain how compressed this timeline is. And I keep forgetting that it's only 2023 that ChatGPT came out. And it's only 2021 that we made GitHub Copilot. It feels like we came so far in such a short time. And so Spec-driven and what was created or was thought of here in the middle of 2023, way before vibe coding was a thing. And everything. So it starts by me having a conversation with Don Syme. If you don't know Don Syme, he was for many years at Microsoft Research and was one of the leads of the F# language. And he decided to join GitHub Next together just after GitHub Copilot came out. And he's a really a smart guy with very interesting ideas. And so we found ourselves with no projects that we had to do, and the charter of GitHub Next was sort of to scout ahead, think about what's the future of software development. Can't you make a new GitHub Copilot moment with a brand new ideas? So I thought, let me try to think ahead like 20 years. What had happened between launching Copilot and this point in time was GPT-4. And that gave us two data points, GPT-3 or 3.5, which is what we launched with Copilot, and GPT-4. And we could see like how fast LLMs were improving at writing code. And so I thought, well, if I go 10 years out or 20 years out, that's going to completely revolutionize how we write code. I just simply cannot believe that in 20 years we will be writing code by looking at lines of code. That's inconceivable to me. So what will we be doing? How will we write code? And the thought I had was, well, we will be writing code using natural language because that's what fits in our brain. And so we will be specifying what the programs should do, and then the LLM will turn that into executable code. So like, let's call that artifact a spec, and that will be turned into executable code. And then Don Syme, he replied, oh, that sounds interesting and plausible, but he has his feet on the ground and wants to sort of deliver value now and says, well, all of this code that exists today, that's not spec'd. So this won't help that, right? Like that's a neat idea in 20 years, but it won't help now. And so he wanted to think about how can we do something for all of the programs that exist today? So could we go the other way? Could we make specs from code and then look at those specs and then go back to code? And so he sort of immediately abstracted it into this strange higher order world where you had a duality between these two things. And so I was a bit like taken aback and thought, wow, that sounds interesting, amazing, but as a completely different project. And so that's not exactly what I'm interested in. I'm interested in exploring this spec world. But Don is the kind of person who can't help himself, so he went on to build his project. And he called that first, he coined it extract, edit, and apply, EEA. So the idea is you generate a spec, and you throw it away after the whole thing is done, but you generate a spec from the code right now, then you edit that spec, and then you turn that back into code, that change in the spec. So you have a thing. This is, by the way, inspired by his original slides about a thing and a change thing, which I thought was hilarious. But this is, of course, a piece of software. And then I consider this like a projection. You project along a topic, let's say the authentication system of this web app, and then you get a specification of what does the authentication of that app look like. Then you change it because you want to change, I want to use SSA or something like that instead of whatever is now there. And so now you have these two data points, a spec and a change spec, and that change the LLM sort of projects back, it blows up back again into changes to the code. So that was the original idea. And I think this has some like beautiful theory. You could almost cast it in like category theory language and so on. But it was very, very hard to get right. When they wanted to turn it into a product, it turned out it was really difficult. It took at least a year, to get the user experience to feel good, and we also needed a slightly better models. But it was eventually shipped under the name Copilot Workspace. Has any of you heard of that? Sort of a project that came out of GitHub Next as an experiment in April 2024. And eventually it was sunset because we wanted, GitHub Next decided that Copilot agents was the future, and so it's not under development anymore. But what you can say is that in current terminology, this is very, very similar to task-based spec-like approaches like Kiro, which you maybe have heard of. So in the meantime, I went on to build Spec-lang. So here I have the spec first and the code is second. So in other words, the idea is that the programmer, the human programmer, writes a spec for their entire program. This is what they develop. And then this is what they store in version control. This is what they share with their colleagues. And then the LLM turns that into code that can be executed. And so the developer never looks at executable code, but they have to think like a programmer because they have to structure their spec right in order for the LLM to have a chance to build executable code. So what we did with the Spec-lang project was a very small team. It was essentially me and another person. So what we did was that we had to focus very heavily on something, and we chose UI-heavy apps, like mobile apps, in fact, so that we could like make a nice demo. And that the advantage of a user UI-heavy app was that then you don't have a problem of sort of determining whether the program was correct afterwards, right? You just look at it and see, oh, does it look like it? Does the button work? So it's very easy to have this, like, does it work yet development loop. So that was the project. It lasted for about 7 months, and the learnings we took from that was that the models weren't there yet. Back then, this was very early GPT-4, and they simply weren't good enough at writing code yet. So most of the time on the project was spent on model limitations like, oh, the context window is only 4K, and when we're compiling multiple files across the project, then they don't match up. And so we did all sorts of shenanigans to try to make that work. Then there was another mistake, which was that I should have just started by saying, let's try to make small apps work. Like find us a corner of the development work, which is small apps, and then we can spec those out, and then the context window and cross-file dependencies wouldn't be such a big problem. And then another mistake was actually the UI-heavy stuff, because it turns out like when you're building UI-heavy things, the UI is what you care about. You care about exactly the placement of the button and the look of the button, and that's very cumbersome to spec out, in fact. And the model gets it wrong all the time. So we should have leaned into what the model was good at, which at the time was like Python scripts. But I think on the whole, what I took away was I still believed in spec-driven development, which wasn't a term back then, but which this was. We just needed to give it more time, we needed better models, and we needed a bigger sort of effort in producing the thing that turns the specs into programs. Okay, this is a small screenshot from a demo we made, where you here see a spec of a very small app that looks at that is supposed to be a mobile app that shows you Hacker News stories. And then down here is the renderer that sort of keeps an eye out on whether the spec change, and then recompiles the part of this app that needs to change. And so I had this live demo where I would change the right align score on author to left align, and then a moment after, this one would jump over here, and it was very fun. Okay, so let's get back to this question I started with about the 10x. So LLMs are incredible at writing code. So how do we use them to really massively speed up software development? And to my mind, the answer here is not about the LLMs. It's all about the humans. Because if you want to speed up software development by 10x, you have to think of what is the bottlenecks becomes the humans that at the end of the day have to sort of decide what software we are developing and how it should work. And you're simply not able to 10x the code complexity you cram into people's heads, right? We're already maxing that out. So somehow you have to compress the cognitive load of the systems inside the human's head. And so that's really your task. And then you have to make the LLMs work with that under those constraints. And so I think that's not dissimilar to something we've done before in software already. So I made this graph here where if we define 1x software development as software development in any modern language, then, well, that's at least 10 times as efficient as developing software used to be in assembly. So we've already 10x'd it once, and the way we did that was by moving from how the machine thinks to how the human thinks. So that compresses the cognitive complexity that the human has to care about. And what we have to do is the same kind of thing. We have to find the thing that compresses the cognitive complexity for the humans. And I posit that that's specs, the right kind of spec language. And I claim that vibe coding is not there yet, right? Like, you can argue all day about how would you even measure something like this, but I think my message here is that I don't believe that vibe coding is anywhere close to 10xing software development. Right? It gives you a boost, it gives you a speed up when done right, but there's still far to go. And so the claim I'm making essentially is that if the human developers ever at any point in the software development lifecycle has to look at the executable code or care about it, you've lost your 10x. That's not possible. Like, that will become the bottleneck. So I think now I mentioned vibe coding and I've mentioned spec-driven development. And so those are two different ways of doing AI-assisted development. And I think you can sort of simplify the world by painting a one-dimensional spectrum here, where on the left you have like pure vibe coding. ChatGPT, please give me the code that does this, and then please change it like this. So that's what Karpathy was talking about when he said vibe coding, right? Really short prompts, changing them. And then what is much more popular today, I would distinguish that from vibe coding. I call it agentic coding, which is like Claude Code, Codex, and which is characterized by usually you spend longer time explaining what it is you want. You have a longer prompt, and the agent implements this. It does its own testing. There is sort of like a harness, a loop that does things. You review that, you adjust. There is like a short interaction loop. And then that finishes your PR, push it up, you merge. I think there is, further along the axis, you have task-based specs, where you sort of make a long prompt about what you want, and then the system generates a spec for this new task. And so there's a new artifact in the middle that wasn't there with the agent, which is this task spec. And then an agentic coding loop takes over and implements this spec. And then you probably keep that task spec around afterwards for review, like sort of like that can go into your repo as sort of a documentation. And so there's at least Kiro, which does this, which is still on the market, and then Copilot Workspace sort of fits roughly into the same sort of category. And then at the very far end, we have what I call pure spec-driven development. And here the difference is that the spec is first. That's the document you write. That's what the human sees. That's what's get implemented into code in a test, with tests and a loop that sort of makes sure everything is done before it returns to the human. And the whole point is that the spec is the artifact that you keep. That's what the human cares about. And so that's where SpecLang fit in, and that's where CodePlane fits in too. And there's another startup by Andrei Breslav, famous from Kotlin, who called CodeSpeak, that is sort of going in the same direction. And I think some high-level words that sort of fit on this end of the spectrum are that it's very quick to get going, very low sort of activation energy. It's really great for use once code, and that's at least a feature. Like, and then you can argue how good, like, yeah, okay, so it's very good for use once code. Let me stay there. And your harness around the LLM, the software that needs to be around the LLM, is very simple. It's not so complex. Over here, I would say that the feature is that this is a much more controlled and predictable process, right? You're saying what the program should do very directly in the spec with the requirements, and these are maintained, and so that's control. And I think there is a bigger focus on the whole software development lifecycle being sort of embedded into the flow. And another trait is that the system around the LLM is more complicated. It needs to do more stuff for this user experience to be good. So I mentioned the software development lifecycle. I think the sort of the middle part of the development lifecycle is the iteration loop, right? That's actually the most important thing. When I think about what makes software developers more efficient, I'm not thinking about the greenfielding part. That's not important. We spend all of our time almost changing an existing piece of software, iterating on it. And so I spent a long time on this slide generating 200 pictures with ChatGPT because you can never like get the picture you want. It's an example of vibe generating pictures being difficult. But have you ever had like to oversee a big construction project in your house or apartment? So there's like two major ways you can do that. One is you agree with the contractor what you want built, and then because things show up and changes happen and you realize something you hadn't considered, like you have this, oh, by the way, the cupboard should be over here, and by the way, that window should be a bit bigger, and by the way, there should be a tower here. And so it turns out at the end of all that, what you want becomes like a very long list of changes. And so what can easily happen is that the contractor loses oversight of the whole like story that you want, and he starts taking decisions for himself, and they were not the decisions you wanted, and so something weird turns out. And then there's another model of where you sort of very careful, you carefully make like a blueprint. This is what I want, and then when changes occur, everyone makes sure to change the blueprint, so that you always have a document which is this is what it should look like at the end. And so I think this is spec-driven development, and this is sort of a bit like a caricature of vibe coding. Well, yeah. Anyway, don't take it too serious. Like silly pictures generated by ChatGPT, but I want to delve deeper into comparing agentic coding with spec-driven development. So I'm going to take like a few touch points of elements of the software development life cycle I think are important. So the part about talking a bit again about iteration, the thing that's not always thought about is the thing we always think about when we're making a prompt to an agent, or when we want to change something in the system and we're talking about it in a meeting, is what needs to change. What we don't always talk about is what shouldn't change, what should stay fixed. And this can be a problem because then the LLM or the person that carries out the change that you want is not aware of what they cannot change. And so maybe you are not aware, they behind the scenes are changing something fundamental in your system. So I think that's a risk you run with agentic coding, that the LLM doesn't retain the things that you thought would be retained. And so you can test the program afterwards, you can go look at the code, but if you do that, then your 10x software development is certainly gone, right? You can hope that the LLM guesses your intent, but that's not control, right? That's not predictable software development. So the way that spec-driven development is different from this is that you directly go in and edit the requirements or add new ones. And all the ones you didn't change, they're still there, right? They're right there. So the LLM knows that those shouldn't change. We still need those. And so when it generates tests, which it should, then it generates tests that satisfies all of the requirements, including all the old ones. And so that has the consequence that also the conceptual model of your system remains, because that's very explicit in your spec. What is the conceptual model of your system? So this is just like reiterating that I think any complex endeavor that human engineers have ever done, it's achieved through a careful process of analysis and prediction. Like we have control over that process. So this change I will do here will have that effect. Otherwise you cannot build skyscrapers and send people to the moon. And so putting it out on a limb a bit, I think it's the same with software development. You will not be able to build complex software system by hoping that it can guess. So the next touch point is that software development is really about collaboration between a team of people. And so there's 3 headlines here: onboarding, parallel work, and code sharing. I want to quickly mention. So onboarding, you have a new team member joining or someone moving into your code base. And for agentic coding, how will they do that? Well, if your software development is driven by agentic coding, well, you can get, you have to imagine that the system is now so big, right? We are accelerating software development. So it's much bigger than code bases are today. So what will they do? Well, you could auto-generate docs, I guess, using an LLM. But how are you sure that they got it right? You can read the code, then you lose your velocity. The third one is it's slightly different kind of tact, but I think that there is there's no there's no good best practices for how we do agentic coding, and everyone does it in their own way, and so onboarded people, they have to be sort of carefully told how do we do agentic coding here. I think the difference with spec-driven development is that the idea is that the spec is now small enough, it's cognitively compressed so you can read it, and it's structured so you can understand it, and it's made for human consumption so it's pleasant to read, and so you sort of onboard people like you do today. Then the second point is, how do you work in parallel? Two people making two PRs, and then you want to merge them. And how do you merge two change sets that came out of agentic coding sessions? Do you ask the LLM to merge them? Well, how does the LLM know how to merge those two sessions when it wasn't specified what the sessions were really about, right? It came out of a conversation indirectly. And so it was two different conversations, and it's very unclear how they overlap. Or the human could merge the code, but then the human has to care about the code and you're dead again. With spec-driven development, the human can merge the spec because it's compressed cognitively, and the LLM just regenerates the code. So merging just works like it does today, except that you're merging on the level of the spec. And then there's code sharing, which is like you're writing a library of something. So if you're writing a library agentically, then what is the API? You have to sort of specify that somewhere. And you have to make sure that agentic loops don't change that API. So how do you make sure that's preserved? Well, you can look at the code, then you're dead again. So with spec-driven development, the API that's written really strictly in the spec, so you know it will be preserved. So this is just like my last point, sales point about spec-driven development, is that I've sort of contrasted agentic coding or vibe coding against spec-driven development, but really they're not mutually exclusive. Rather, I think spec-driven development can be seen, that should be seen as a form of programming, and the spec is the program. And that means that you can use all of the LLM-powered tools to change those specs. So you can vibe code on specs, you can do agentic coding on specs, and then you review the specs afterwards to make sure that they got it right. And the problem is that if you try that today, it won't work so well because the models are really poor at writing specs. They will be chatty, wordy, they will be verbose, it won't fit the style of what we want for good specs. But that's just a problem because spec-driven development isn't big enough yet and the models haven't been trained on it. Once there are a few thousand programs out there with good, concise specs, then models will know what spec-driven development means and they will be good at writing specs. So that's what I wanted to say. So to sum it up, LLMs today are amazing at writing code. I think we can all acknowledge that. But writing code is not the same as software development. And so we need to think about, it's not trivial to turn that capability of writing code into something that accelerates software development professionally in practice on big systems. And my claim, fundamental claim, is that if we really want to harness that power and 10x software development, then we have to move to a place where the developer doesn't look at the code. Otherwise, it's not possible. It won't fit in our brains. And I think spec-driven development is the best way forwards for that. And it allows us to care about specs instead of executable code, and that's cognitively compressed. It allows us to control and predict what changes will come to our program by changing the spec. And it allows us to collaborate effectively just like we do today on the level of code, but just on the level of specs, which is like allows us to be more productive. But all of those things can only be unleashed if we have a good system for this. So we need a language for specification that supports that we write clear and unambiguous specs. We need a system, a harness around the LLM for generating the code from the spec, generating the test, looping in the right way, being efficient and fast at this. And that needs to provide a user experience that gives you the right kind of feedback when you accidentally write specs that are self-contradictory or in other ways cannot be rendered. That's it for me. Thank you.
Thank you, Johan. Now it's time for questions. Does anybody have a question for Johan regarding the presentation?
Yeah.
So when programming, in terms of how precise you are, in every program there's a trade-off. There are parts where I really don't care, and there are parts where I really need to be very, very precise.
Yeah.
So when doing regular development and AI-assisted development, I have the trade-off. I can make the trade-off. I can let the AI do something and not read it, or I can go down even to writing it manually, like primitive person.
Right.
Where's the trade-off? I don't understand. Where's the trade-off with spec-driven development? How can I go down into precision without accidentally reinventing the program?
So I think that spec-driven development is naturally lends itself to exactly that. I think a good image for how writing a spec is that you start with a big block of marble, and then with a few requirements, you sort of get the rough shape of what you want. And where you don't care, you're not chiseling out all of the details and every single strand of hair on whatever figure you're chiseling out. You're just leaving it there with the rough shape. And the model will come up with a solution that fits the requirements and which is good enough. And then in the parts where you really do care, like you can make a lot more requirements that really fix the behavior in the specific way. And sometimes it will even be convenient for you to write it in pseudocode. But those are like the very, very core inner loops or very specific parts of the API or something, right? Where everything has to fit in just the right way. Does that answer your question?
Yeah, it kind of sounds like you would end up reinventing some high-level programming language, but that's small part. There's the part that I can't get my head around.
Right. I mean, you could have a system that either you could just do it in like some pseudocode you make up because the LLM can understand it, or the spec system you're using has like a recommended way for you to specify things in that level of detail. But mostly, I think the vast majority of the time, you can create the easiest way for you to make those details is either by specifying a few more requirements or by saying it has to fulfill this test. Like it has to fulfill this input-output pair. Right?
So I'll actually do a follow-up and ask a question. Rather than asking, it's actually my question about 6 months ago. And then about 2 months ago, I stopped asking that question because I haven't really written any code for the past 2 months. So now, like when I need to go to the nitty-gritty, I still write English, and I just write more detailed English, so I can actually relate to what you're saying. However, there's still one thing that I don't quite get, and that's the contracts between different libraries. So I'm still operating maybe, within a logic. And Cloud Code right now is amazing. You can write these modules or changing it anyway. But even then, when I have to tell it how to establish interfaces between modules.
Right.
I don't have it. To be honest, I have a solution for this, and
Right.
it seems like Meteor does both. Because like when he tries, it usually fails. So that's kind of like my first question: like, how do you bridge modules? How do you bridge these contracts where it just doesn't seem like? So the way that these high-level programming languages are built is that you have a dependency tree, you have module structure,
Right.
and it still has to work that way.
Yeah.
And,
Agreed.
It was made so that humans can make these connections. So that would be my question, and maybe like the same question, but looking at it from a philosophical perspective. Because you gave us the example that we started from assembly, and then we created higher order languages, and then we need to go even higher and get to spec-driven. To be honest, I don't like that parallel. I've never liked it because I don't actually see it. Because higher level languages still have compilers and interpreters, so they're highly deterministic. And anytime we run them, we get the same thing. It's not the same thing with LLMs. You get temperature and sampling fire,
Right.
so that you get good code out of it, but it stops being deterministic. So basically, these two put together. So how do you be specific about contrast between modules in an environment that's not deterministic?
Okay, let me try to answer the question. So there's really two questions, I think. And the first one is about how do we get to reusable software in specifications, like that you can librarize something and you can use it elsewhere. I don't think anyone has the full solution here. But there are various approaches that sort of are shaking out. So there's a guy. He's not. It wasn't even for spec-driven development as such, but he tried. He has a blog post recently. I forget his name, where he spec'd out a small library for. I think measuring time or something, or printing the date or something like that. A small thing that sort of exists in the C standard library and exists in all standard libraries in all programming languages. And it was just spec'd out, and then you could sort of compile it for any language you wanted. And then, so you could imagine that libraries were transported as specs. And then as part of compiling or rendering your big program, which depends on something else, it renders everything into it. So that's really reminiscent of compile time linking in C and C++, right? Where you need access to everything, all the header files, when you're compiling a program so it can deep link into it. So it's not completely dissimilar. So there's a lot of disadvantages to that in terms of amplifying the instability of the recompilation, which is the second part of your question. How do we is it even reasonable to sort of put that line there saying machine code, Python, specs? I think to a large extent it's a technical implementation detail that compilers are deterministic. Like, what matter would it do to you? How would it matter to you if GCC was non-deterministic? It wouldn't matter to you. So well,
it's the most important aspect of it.
But it's not deterministic.
But
it
100% preserves the properties I care about.
The function.
It preserves the properties you care about. Yeah, so that's important.
Steps, and each one preserves the important property 100% of the time.
Yeah.
The end of the pipeline is 100%.
Right.
If each step preserves it 99% of the time.
Right. There's an amplification.
You have 36% chance of getting the property at the end.
Yeah, if you have no correction during those 100 steps. So that's a necessary part of a system like this, is that there is a correction that makes sure that you do not deviate.
There is a recent paper, Million Steps, fully deterministically done by LLM. So we can share on Discord. And the paper is highly interesting. So basically, they managed to replicate 1 million steps fully deterministically.
Temperature zero?
It doesn't really matter. The key part is error correction.
So the temperature 0 versus non-zero temperature, people shouldn't over-index on that. Because even if you have temperature 0, which, let's assume that temperature 0 actually meant deterministic, which it doesn't for very technical reasons about how GPUs work. But even if that was deterministic, you're running on a manifold which is very, very unstable. So you make a very tiny deviation, then you can you can deviate arbitrarily far. And so what you really want is predictability. And determinism is not exactly, that doesn't give you predictability. And yeah, okay, yeah.
I have sort of in this line of questioning. You mentioned unambiguous, right? And I think that's very important. So if you can unambiguously, if you can unambiguously design it, that's fine. But what about conflicts in your stack? So I think this is the biggest separator for me in this line. Higher level languages allow for conflicts, lower level languages don't, right? Or like, have you thought about this? Like, let's say it's very easy to make a conflict in a spec that will only show itself once it's in the implementation layer,
Right.
lower level language, but it's not really going to be immediately obvious, especially if you don't even know the lower level language.
Right. So I think this is an example of where we're putting a big burden on the harness, the renderer that takes specs into code, where I would say that's a problem for that system. That system has to detect the conflict. For instance, there's a type error, or tests fail immediately when you try to run the code, and then it has to translate that back into the world you care about, which is the specs. And so that's not an easy task to do, but if you gave any one of you this task for a given system, you would be able to do it. So I believe LLMs will be able to do it.
I think it's more of an intent problem, right? Like, if we know what's going on, we can solve it, but the LLM doesn't know what we want, or like which one of the two conflicts should prevail.
It cannot resolve the conflict for you, but it can return to you that here is a conflict. And it can give you advice on what it thinks is most reasonable. But it doesn't necessarily resolve the conflict for you. I think this is very similar to, like on GitHub, if you have an issue and you ask the Copilot to fix the issue for you, then since it doesn't have any intent of the system and it doesn't have, it will oftentimes give you the wrong solution to the problem. Yeah, the problem goes away because it sort of deleted whatever, or it disabled the code or whatever. But it's sort of like you could have a system that at least makes you aware of the problem. That's the first step. And then the second step is, can it give you good advice on how to proceed? And maybe you could even imagine, like, most of the time, if it's confidence and you can trust in the confidence, it can resolve it automatically. And you can think of ways of handling this. That's what I mean with a nice UX loop down here. That there's a very high burden. I think, as opposed to compilers, GCC, which has a terrible interface with a gazillion flags and so on, then there is it's like you cannot in compilers you can separate the IDE and the renderer. You can separate those a lot. and say, well, my language is well designed and I can create a compiler for it. And then I create an IDE for that language and I compile. And so there's a clearer separation where I think for spec-driven development, to my mind, they are more intertwined, because the specification language, that can be a nice philosophical exercise, but if you cannot demonstrate that there is a good UX loop, it's not a good specification language, right? It doesn't work. I think he was first.
Code is very specific. It's exact. It's the perfect spec language because it's, you know what it is. Why would I want to use a human language like English, where me saying I love you needs to have like a long paragraph explaining you the nuances that I'm thinking of, and everybody is thinking different things. Why would I use a human language instead of something that's more specific, exact? Because
right, I think that's a great question, but I would try to answer it by saying, well, it's for the same reason that we're not using mathematical syntax for everything we are expressing. We are not writing legalese in math language. We're writing it in human language. Not that it's very readable, but it's like, and we are, if you read a math paper, most of it is words. And there's a bit of it that's equations. And I think it's because first of all, you don't need to be executably exact with everything you're saying. Because most of it can be derived from like a shared software cultural set of assumptions. And the other one is that the human mind is evolved around the way we use language. Like those two things fit together, and programming languages are they are artificial in the same way that mathematics is artificial, and we have to very carefully be trained to think like this. And we can, because our minds are wonderful, but it is not the natural way we think about it. I challenge you to have ever had a conversation with another programmer about a piece of software, and the first thing you did was to start writing UML diagrams and code. Like you're going to write, and when I said UML diagram, I meant the executable kind. You're going to write, start waving your arms and say words. That's the first thing you're going to do. And then once everyone is on the same page about what the words mean and what's the arena and where are we, then you write 2 lines of code. Because those are the critical part that needs to get absolutely right. Everything else is words.